In section 14.8, we explore Baxter Kinematics. As we mentioned at the beginning of our chapter, Baxter has a 7 degree of freedom arm with a wrist point but not a spherical wrist. For more on spherical wrists, please click on the link. This means we cannot reach a straightforward analytical solution. But if we do assume that Baxter has a spherical wrist, then what we get is an approximate analytic solution that when we use the forward kinematics, the Cartesian pose for the tool or the end effector is just approximate. There is an error, particularly in the pose of that wrist from where it should be in the exact location. This approximate pose and accordingly joint angle configuration can be used as a seed or an initial guess to numerical techniques, such as those from KDL or TrackIK. In our package Baxter FKIK, we have a number of files and techniques that allow us to run both forward and inverse kinematics. Anytime we compute forward kinematics, we're going to do so from the torso as the base frame to the right gripper. The right gripper is Baxter's default end effector frame, better thought of as a flange. Now, the forward kinematics package can be adapted to use different kinds of tools. That means the Baxter robot actually comes with a set of fingers, some which are longer, others that are shorter, and also some custom-made tools. All of those can be adjusted with a transformation within the code. Also, the order of transformation, we use a fixed transform from the torso or the base of the robot to the shoulder frame. This helps us to conform to Denevet-Hardenberg conventions and then follow DH methodology for computing forward kinematics. As part of our code and all the different CPP files, we're going to have two methods that help us resolve forward and inverse kinematics. For forward kinematics, we use the Baxter forward solver method. Here, within the solver method, we have a key function called forward kinematic flange with respect to torso solve. And this particular method will take in a vector of joint angles, current joint angles, and then return an eigentype affine 3D transformation or 3D object, which represents the pose with respect to the torso. This forward kinematic computation is very fast, precise, and well behaved. For the inverse kinematics, we have the Baxter IK solver. Within that method, we have this function IK solve approximate with respect to torso. This function takes as an input that desired pose that you want the flange to have. It's an eigen affine 3D. And then as an output, you're going to get a vector of solutions of possible joint angle solutions. The return argument of the function is actually the number of viable IK solutions. This is an analytic approximate solution that assumes a spherical wrist, and we get more than one solution that are indexed with respect to samples of joint angle Q0. If you go back to our previous lecture, you'll remember that in our planning, we considered the null space of the robot. So the null space is taking a particular joint that we can vary or sample different angles of that joint and still compute a set of inverse kinematic solutions for that. So here we can sample joint Q0, which is the shoulder, and find a number of inverse kinematic solutions. We sample that joint angle every 0.05 radians, and at each value of Q0, we can get up to 8 inverse kinematic solutions. Please click on this link as to why there are 8 possible solutions. Within the Baxter IK solver, we also have a second method called improve the 7 degree of freedom solution with respect to the torso. It's similar to the previous method, but here a second argument that is additional compared to our previous lecture is this vector 7 by 1 Qn. This vector Q 7 by 1 is the seed joint angles vector that we would get from our previous function. And the function will return true or false if it's able to find a better solution. So here we have an assumption that the seed joint angle configuration already has a desirable angle for Q0. It also, what the function will try to do is move the actual wrist point closer to the desired wrist point. Remember that previous to this point, we only have an approximate solution. So there's a small error between where we are and where we want to be. The wrist point error can be computed using forward kinematics. And then from there, we're going to get a 3x3 Jacobian that relates angles Q1 to Q3 with respect to the current position x, y, z. Once we do that, we can invert the Jacobian and use a numerical gradient search to find better values. The details of computing Jacobians, inverting Jacobians, and doing numerical gradient search are outside the scope of this slide, but again, you can click on these 2 links to understand more about the details of such techniques. Now, to actually use the forward and inverse kinematic solvers, all of that can be done inside the Cartesian planar package. In our previous lecture, we introduced planning packages and touched briefly on the UR10 and the ARM 7 degree of freedom. The Baxter also has an equivalent planner, and here we are just listing it for reference, but it will be your task to study that in detail as part of your homework. And the Baxter Cartesian planner is using the inverse kinematics approximate solution in several of the methods for planning. For example, in Cartesian path planner, we'll use the approximate solution, and Cartesian path planner delta P will also use this approximate solution, and also in the joint space path planner to affine goal, we'll use this solution, this solver. And then secondly, we use the improved version, improved 7 degree of freedom solution with respect to torso when we do joint space path planner to affine goal here. So once we want to get to a goal, we'll do the approximate solution first and then the improved solution second. We can also use this method in the refine Cartesian path plan. We're not going into the details of the code here because it's extensive, but this is something you should look back at home.